been working in, I'll start with what Andrei said in the last sentence. I've been working in more than one systems. And my purpose today is to actually give you some, not too specific results, maybe not the latest results, but some more overview of this area that I find exciting. Let's make sure that I have the time here next to me. My general title is on, it will be on the dynamics actually, or on skyrmions, and also of what we call topological trivial textures, skyrmionic textures or other textures. Yeah, so they, let's then move to the first, to the beginning. I'll focus on ferromagnets. Ferromagnetic skyrmions are nowadays the most famous skyrmions. And let us talk about magnets, about ferromagnets. A ferromagnet is described by the magnetization vector. Let's call it M. It's a vector function of space and time. And the special thing is that this magnetization vector is supposed to be of constant, of fixed length. We set it to 1 for simplicity. And that's obviously because if you have magnetic moment in an atom, this cannot change in magnitude, but it can only change in direction in space. So it is only free to point in different directions in space. Well, more formally, you'd say this, this function M takes values on the unit sphere. Now, it is an impressive fact that just from this basic, obvious geometrical property, we can always say a lot of things about magnetization configurations. For example, all magnetization configurations are characterized by a skyrmion number Q, we call it a skyrmion number, which is actually a topological number, a topological invariant. What it does, it tells you that, well, okay, you have a magnetic film. Now, in this magnetic film, the magnetization points in different direction in every probably point. You take all these vectors and all of them point on the magnetization sphere. Now, do they cover the sphere or not? Do they cover the sphere once, twice, 3 times, etc.? They will cover the sphere, either not cover it or cover it once or 2 or 3. This is an integer number, and this is counted, this is measured by the skyrmion number Q, which luckily has an integral form. So you take the integral over this quantity, which you would call the topological density small q. You integrate over your film, your 2D space, and that integral will give you guaranteed an integer number. So that's already, I think, a very impressive thing for people who see these things for the first time. And now let's take a specific configuration. That one here, you would call a skyrmion. How does it look like? Let me explain you what you see in this picture. You have the magnetization vectors. These are the vectors are the magnetization vectors M in every point in your film. But because this is a 3D vector, it's a bit difficult to draw this. Therefore, what we do, we draw only the projection of the vector on the plane. And the third component of the vector, the M3, which is perpendicular to the screen, it is color coded. So this red color means that the vector points towards the screen, and the white color means that the vector points towards us. Therefore, all vectors are equal in magnitude, but you only see here their projection. You see that in the center, you point towards the screen, that is to the south pole of the magnetization sphere. Outside here, you point towards us, that is to the north pole of the magnetization sphere. And in between, you point in every point in the sphere in between. That is, you cover the sphere once. That's why this has a skyrmion number 1. And as I said, can be calculated formally by this integral. You call this a skyrmion. Now, this is not the only possibility. This is an axially symmetric skyrmion. because anywhere you look in space, radially, you see this, azimuthally, you see the same thing. But you can also construct this one, which, as you see, the colors are the same as that one. So you point in the south pole of the sphere here, and the north pole of the sphere here. In between, you point everywhere in between. But if you go, for example, in a circle around this center of the skyrmion, while you circle around in real space counterclockwise, you see this vector rotating opposite to you, so clockwise. So you see this vector pointing that way, and that way, that way. So it rotates clockwise. Now you call this an anti-skyrmion. It has a skyrmion number Q -1, although this is a convention. The sign is a convention. So that's a skyrmion, another skyrmion. I hope I gave you a first impression of what we are talking about here. What are the magnetization textures that we are discussing? Now, let us focus first on the simplest cases. We already talked about the skyrmion. I already said that this is an axially symmetric configuration, but let's make it a bit more formal. To make it a bit more clear, formal, then you describe this vector M by the spherical angles theta and phi. You are on the sphere, so you can take spherical coordinates, theta and phi. You're on the unit sphere, you don't need the radial coordinate. Now, when we say axially symmetric configurations in this context, and we're discussing now the plane in rho phi polar coordinates, this means that the theta angle, the polar angle, is an angle of the radial coordinate only, theta of rho. And the phi angle of the vector, of the magnetization vector, is equal to the phi, the polar coordinate, plus a constant, probably. For example, if you are here, you are on phi small equals 0, polar coordinate, but the vector points in the y direction, that points in the p/2 direction, pi/2 direction. So that's here, 0 plus pi/2, the capital phi of the magnetization vector is pi/2. And then if you rotate around, you rotate together with a small phi, with a polar coordinate phi. I mean, the vector of the magnetization rotates together with a polar coordinate phi. So this is I just explained once more the skyrmion. And to complete it, let's say that this phi, this theta at the center is pi, that is south pole. The theta away right here in the white region is 0, that is in the north pole. Is this the only possibility of an axially symmetric skyrmion? No, because you can also construct this one, which is more complicated, but it is interesting. So in the center, you point in the vector points in the north pole. Then you go out, here it points in the equator of the sphere, here it points to the south pole, this red region, but then again turns around, points to the north pole. This is axially symmetric again, because wherever you look in the radial directions, all radial directions, you kind of see the same thing. But we would call this the skyrmionium. Why? Because if you're in the center here, you kind of see a skyrmion. And then if you look from here outwards, you see another inverted skyrmion. So this is like a positronium, I mean, you know, a skyrmionium. It is a particle-antiparticle thing. It's a skyrmionium. Now, it also has, to make this complete, it also has skyrmion number 0, because it is like two skyrmions with opposite skyrmion numbers. You kind of cover the sphere and uncover the sphere. So that's skyrmion number 0. Skyrmion number 1 or skyrmion number 0, the purpose of this talk is to show to you that this is a very big difference. Now, let me go to some equations, and just to say, well, relatively simple equations that we're not going to use too much, but it's good to know that this system is a physical system. It has an energy. The energy has three terms in this case: exchange, anisotropy, what we call the M term. So the exchange interaction is a very typical thing. It shows up in many systems. I mean, whatever system you're working, probably you have seen your system, this kind of energy term. This is the derivative of the magnetization vector squared in every direction in space, and mu is 1 or 2 directions in space, and that's now the exchange energy. Because we are in a condensed matter system, we have some kind of anisotropy, probably because of the crystal structure, etc. So we have the anisotropy energy here, which we choose here to be in the third direction, perpendicular to the field. So if you have the M3 component of the vector point perpendicular to the field, this is a good thing because you reduce the energy. You have a minus M3 squared. That's a coefficient. And now we have this special term, which is there in magnetic systems. And I'm sure it's there in other systems as well, but it's become kind of famous in magnetic systems in the last at least 15 years. This is an exchange term because it contains a derivative, but it has a bit of a different physical origin than that exchange term. And it is different than the first exchange term because this has one space derivative. That means that it matters where you move from left to right or from right to left, whether your magnetization changes in some way from left to right or from right to left. It's a chiral term. So this is now a chiral exchange interaction. It is called the Dzyaloshinskii-Moriya interaction because it was introduced by these people in the 1957, 1960. So this is now a quite important term. While this term favors the direction perpendicular to the film, this one favors the uniform magnetization. That is, it doesn't like to have derivatives because that's zero if the derivatives is zero, so that's minimum. But this one likes to have derivatives, likes to have changes in the magnetization because you can always make this derivative or this term negative by having a derivative, by having a change in the magnetization. So that sounds a bit strange because we're in a ferromagnet, which is supposed to be polarized, spin polarized. And what we're saying here is that this Dzyaloshinskii-Moriya term actually does not want you to be polarized. It wants the magnetization to have changes, to have variations over the material. But that's how it is. Okay, I don't think we need to keep in mind these expressions, but we just need the flavor of that. Up to this point, well, I should probably say that the skyrmion, the skyrmionium that I showed earlier are minimum energy configurations of the energy that I just showed. We did not prove it, but I'm just saying it is, they are. People find this numerically. It's more difficult to find this analytically, much more difficult. But numerically, they are minimum energy configurations. They are there, and they have been observed. But what we do now, we take a step and we go to the dynamics of the magnetization. The skyrmion, the skyrmionium were just static structures. They just stay there. Now we go to the dynamics. To go to the dynamics, you have to consider the energy that we saw, and then say, well, this is a Hamiltonian system. Let's write the equations of Hamilton. And this is the Hamiltonian equations, the standard classical mechanics equations. They look a bit complicated. They look non-standard, but that's the interesting thing about the system. So what they say is that the time derivative, the magnetization changes in a way given by this term. Now, given by this expression, this is the M cross product a magnetic field. I think most of the people here must have seen this equation in a form because if you do an electromagnetism course, what you see is that if you have a magnetic moment and you have a external magnetic field, what the magnetic moment does, it is precesses around this magnetic field. This is exactly this equation. Precession is given exactly by this dynamical equation. So this describes precession of the magnetization around this field H. The thing here is that this field H effective is not an external field, it's not a constant, but it is a field produced by the magnet itself. So, and that's given by the energy. So this is the field. So, you know, if you are a magnetic moment, then you basically depend on the magnetic moments in your neighborhood and your dynamics. So I don't want to go into these, you know, explain in detail these terms, etc. But you see that it is M cross product some Laplacian of M, some derivatives of M. It is a nonlinear equation. That's the essence of it. It is a nonlinear equation, a complicated nonlinear equation. Now, the skyrmion and the skyrmionium are minima of the energy, and they are, of course, also, by implication, static solutions of this so-called Landau-Lifshitz equation. So you solve this equation somehow numerically, or maybe analytically if you can, and these are static solutions. Now, people sometimes ask at this point, well, yeah, but there are damping effects in a system. Yes, there are. They are not included here. You can include them, but we're not going to go into that today. They're supposed to be smaller effects. Okay, so now I'll take one more step, relatively big step further, and say, well, yeah, I do have the skyrmion, I do have the skyrmionium, but they are static. Now, can they move? Because if they move, then they are probably functional. They are probably better. We can probably use them to do computations, to come up with schemes, devices that are using them as information bits that are flowing in my device and transfer of information, something like that. Can they move? If I ask this question, maybe the simplest way to put this is to say, well, okay, let's assume that they are moving at a constant velocity v. So m is a function of x minus vt, something propagating in the x direction, x minus vt comma y. So x and v are connected, and it's a wave. And that means that the time derivative is related to the space derivative by this simple form. Therefore, the equation that I just showed, I substitute the time derivative for space derivative. And this is the equation that I have to solve now. How do I solve it? Very difficult. But let me give you some properties of that. Okay, now I try to guide you through some calculations that we are not going to do explicitly, but try to explain them in a most intuitive form that I can. You see, if we have this equation, I can do the following trick. I can take the cross product with d2m, so I have d2m cross d1m, and then the dot product with m, so m d2m cross d1m, and you might, if you remember, this was exactly the topological density. That's why I do it. I construct the topological density on the left-hand side. And on the right-hand side, I wait and see what the calculation gives. And this is what it gives. Well, it's not easy, of course, to imagine this at the moment, but I'm just telling you this is what it gives. On the left-hand side, I constructed the topological density small q. That's why I multiplied by t2m by m. So I have this relation. All right, now, in fact, if you take this relation, this is Q, okay, the topological density, but this one has a nice form because this H effective is just the derivative, the functional derivative of the energy with respect to magnetization. Oh, all right, now, if this is so, we have an interesting relation here. I can integrate this, so I can integrate the integration of topological density because I want to take the topological number and integrate the right-hand side. But this is just the derivative of the energy with respect to a space direction. Well, but the energy, my film is homogeneous, so it does not depend on space, and therefore this is zero. So I get now the relation that the velocity times the integral of topological density, which is the topological number, well, multiplied by 4 pi, but this is not important, is equal to 0. You see, well, okay, you might follow to some extent this calculation or not, but the result is that the velocity times the topological number is 0. So let's look at it again. Velocity times topological number is 0. Now, this is a link between topology and dynamics because it tells you that if Q is non-zero, if you have a topological skyrmion, then necessarily the velocity should be 0. So this, in ferromagnets, topological solitons cannot propagate as waves, as solitary waves. On the other hand, if you have a topologically trivial Q equals 0 magnetic soliton, then, well, I don't know, because that would be 0 equals 0. Okay, fine, that's okay. So I don't know, but it may have non-zero velocity. So that's the result. In fact, this is a very precise result. This is a possibility. It's not a result, it's a possibility. So this is now a very direct and very simple, in fact, link between topology and dynamics. And this is very general. I mean, the calculations that I did in the previous page are straightforward. I mean, of course, we cannot do this out of the top of our head, but they are simple calculations. Now I'm getting to you know, the previous calculations that I showed are they are heuristic and they are not so precise. You know, I might be wrong, so that would have been kind of not correct, but they can be made more precise. And here I have a slight technical part that I think I will follow this and go relatively. I mean, normally it should take a lot of time to present that, but I will not take too much time. And I would ask you to bear with me for a few minutes as we go through these calculations, and then at the end we'll get the results and we can go to examples. But I'd like to show that things can be done, and on one hand, they can be done precisely. On the other hand, that if you do this precisely, you do get quite some strong results. So there is a fundamental relation. If you are, you know, a little bit, somebody is a bit smart, then you can take the time derivative of the topological density. It turns out that it satisfies this equation. This is a space derivative of some quantity. Now, this is a so-called continuity equation. It's time derivative and connected with space derivative. Well, that's a standard thing. If you integrate over space, you integrate this over space, and this is an integral over space, the left-hand side and the right-hand side. Of course, the left-hand side, it's just the integral of Q of the Skyrmion number, and you take the time derivative of that. The right-hand side is an integral of, is a derivative, an integral of a derivative. Okay, this is the function at the ends of the integration interval, which is supposed to be at infinity. So this whole thing is 0. Therefore, the time derivative of the topological number is 0. Well, all right, but this is obvious thing. Because obviously this is a topological number, it does not change, it's a topological invariant. So all I'm telling you here is this Q is constant. Okay, we knew that. We have expected that. But we can now say the following thing, that if you take this, what I call the fundamental relation, and you consider this term in the space derivative, then it turns out that this is a space derivative itself. Let's give just a quick argument about that. I'm saying this thing is equal to the derivative of some new quantity that I call sigma. It's a derivative. Why would you believe me that this is so? Well, because this thing is equal to delta E delta M, as I already said, is a function derivative of the energy. And therefore, as I already said, the right side is basically the derivative of the energy with respect to some space. So this is like the chain rule. You know, if you take, this is a nu here, nu. So if you take the derivative of the energy with respect to some x, this is basically the derivative of the energy with respect to its the magnetization times the derivative of the magnetization with respect to the space direction. So this is a derivative of the energy with respect to space. Well, this is supposed to be 0, and therefore it should be a total derivative of something else. Anyway, this is, I'm just trying to tell you that what I'm doing here is plausible. I don't prove anything. I'm just saying arguments. But the end result is that this Q dot is the derivative of a derivative. Let's write it. It's a derivative of a derivative. Now, to complete that, I'll just say, well, if you don't believe me, yeah, here is the explicit form of sigma. So at the end, take this thing, do the calculation, you find it is correct. but I'm not saying here, I mean, I probably shouldn't show this page at all. So for anybody who is, who is into that, probably an expert, I'm just want to say that this is all explicit. While in my talk, I'm just trying to make it plausible, and I'm not discussing the details. So let's move on and say that, you see, the end result is that the time derivative of this topological density is the derivative of something, the derivative of the derivative. So this is a strong result because it tells you that not only, and here I come to, to the basic result of all I'm been talking in the last 10 minutes. This tells you that not only the topological number is conserved, which is an obvious thing, but also the moments of this topological density, that is the x times q integrated or the y times q integrated, are conserved. And this is because of these two derivatives. This is a kind of exercise in derivatives or integrals to show that these are invariant in time. They're conserved, so they don't change in time. And this is now a very strong result, because if you have a skyrmion, and it has some topological density, this x dot q, it more or less gives you the center of mass of the skyrmion, or to be more precise, the center of the topological density of the topological density. It's like the center of mass in a solid body. So here is if you think that the mass of the skyrmion is its topological density, this is the center of mass. So the center of mass does not change. So the skyrmion does not move. That's equivalent to saying the skyrmion does not move. And that's a proof that the skyrmion can never move. And actually any topological texture in this system cannot move freely, of course, right? If you put a force, obviously you will move it, but it cannot move freely as a usual Newtonian particle. If you are now in a topologically trivial configuration, it's like having particles with positive and negative mass. That's okay, because the center of mass it doesn't have any meaning if you have positive and negative masses, positive and negative topological density. This could move. That's not a problem. So here's the big difference. Now I skip a few more details. I hope I discussed enough I gave the flavor of what is the fundamental result after all these, some of them probably complicated calculations. And we have here something which is pretty well established. Okay, so because, as I said, other arguments that I made are not so precise, where probably one could have objections. But this is well established. All the calculations are explicit. Now, let me now kind of go back to qualitative things, leave these calculations behind, and go back to qualitative things and say, you see, this type of dynamics has been noted a long time ago. In fact, in the 60s and 70s, there was a lot of work on what they called magnetic bubbles. And at that time, they used to use magnetic field gradients. An example is here. So a gradient, it's a magnetic field gradient. So the field that changes along the vertical in this direction. And you have a magnetic bubble, which is a topological soliton. It has this skyrmion number nonzero, most of them. And they noticed that the bubbles do not move as you expect along the direction of the force of the field gradient. But they move, they are deflected almost perpendicular to it. That's the velocity of the bubble. There is a book summarizing those results at the time. So it's something that has been discussed, at least experimentally, and probably also kind of empirically has been discussed to some extent. But since we're now having these nice chiral skyrmions, we can study these things in more detail. Therefore, I am having here a sketch of a skyrmion. Now, this is a minimal sketch. This is supposed to be an axially symmetric skyrmion, exactly like the ones that I showed earlier. But I'm not showing vectors because that would be complicated. I'm only showing contour plots of the out-of-plane component, the M3 component of the magnetization vector, and they are circular. So that's kind of simple. They are out-of-plane components. Okay, they are. These dashed lines are supposed to point to be negative values, and the solid lines positive values. So here in the center, you point in the screen, and out here, you point out of the screen. Anyway, this is a whatever minimal representation of the skyrmion. And this is here at the beginning of time. And now you apply a field gradient. The field gradient is in the x direction. So your kind of, this is pushing in the field gradient, the force is pushing the skyrmion in this horizontal direction. You wait and see that the skyrmion, after a while, is moving in the y direction, exactly perpendicular to what you would expect from Newtonian mechanics. So that's moving perpendicular to the force, the exerted force. After a while, the skyrmion is up here, continues to be relatively symmetric, axially symmetric. Now let's follow that. We can follow the center of the skyrmion, that is, well, the point where the magnetization points is in the south pole, and this is the red line. It does some kind of oscillations. Now, if you follow I knew the moments of the topological density that I showed earlier, and I said they do not change in time, they are constant in time. Then now that you apply a force, these moments are not constant in time because you apply force, but they change in a very precise way. This is this black line. It is a straight, exactly straight line that you follow, the skyrmion follows under this force, if you define its position to be given by what we call the guiding center, that is the moments of the topological density that are actually a measure of the position of the skyrmion. It's like a center, as I said, center of mass of the skyrmion. So the result is that the skyrmion with topological number non-zero, we said earlier that it does not move. It is spontaneously pinned if you do not exert a force. And if you force it, what it does, it propagates perpendicular to the force, and in fact, with a constant velocity. Constant velocity, not acceleration. So that's what's happening here. Now let's go to the skyrmionium. Apply exactly the same force to the horizontal direction. So we push it in the exactly the same as before. This is exactly the same numerical experiment. We have the skyrmionium again in a minimal representation with these contour plots. We accept the force, we wait and see that after a while the skyrmionium has moved in the direction of the force, not perpendicular to it. And what's the difference? The difference is that the skyrmionium is a topologically trivial texture with Q equals 0. So when forced, this skyrmionium, we find that it accelerates in the direction of the force. That's completely different than the skyrmion. And then if it accelerates, it's not a constant velocity. It's like a Newtonian particle. And then you can also ask, well, what happens if I stop the force at this point? Well, if you stop the force, what happens is exactly what you expect from a Newtonian particle. It propagates freely after that. Just continues moving. Of course, if you have damping, it will stop moving after a while, exactly like if you throw a stone, you know, but that's now the dynamic. So this is a Newtonian particle in contrast to the skyrmion. Okay, so this is the big difference that I would like to convey to you. And now we could, so somehow that could be, I would say, a complete talk, but we have some recent results. So I hope I do have some more, I think I do have some more time, and I can expand the scope of these studies by saying that the skyrmion or the skyrmionium are not the only top skyrmionic textures that are found in these chiral magnets. An interesting structure is you can construct by taking what we would call, I think, a vortex. You see, you have this configuration. You can call it a vortex because here in the center, the magnetization points, say, towards us in the red region. And then around it, it points all the way around this, makes a complete circle, this vector. And then if you go away from it, it still makes a complete circle. So it's not like the skyrmion that it would reverse point towards us, but it's just flowing around everywhere in space. Now, you can also stick to it another vortex, which is an anti-vortex that is here in the center. In fact, it points towards the screen. It's blue. And around here, the vector, this magnetization vector rotates, but it rotates opposite to what is coming for the vortex. So here, you rotate around the center of the vortex, the vector rotates with you. Here, you rotate around the center of this anti-vortex, the vector rotates in the opposite sense. Now, because this is a vortex and it has, so to say, polarity towards us, it has skyrmion number 1/2. And because this rotates opposite to that, but it has also opposite polarity, it has also skyrmion number 1/2. This is skyrmion 1/2 plus skyrmion 1/2. This complete thing has skyrmion number 1. So you could call, I think you could call it a complete skyrmion. And such structures were introduced about 50 years ago in the context of high energy physics in order to explain the quark confinement in nuclei and in elementary particles, and they were called merons, from the Greek word meros, which means a part. And this is supposed to be a part of a skyrmion. It is another part of the skyrmion. Now, how do you understand that? Formally, you take what is called an interesting transformation. It's called the Möbius transformations. You go in the plane x plus iy, the complex plane, and you take this transformation. This A1, A2 are the positions of these two merons, these vortex, anti-vortex, and then this is transformed to this thing here, which looks like a skyrmion. It's not actually symmetric, but it has the general features of skyrmion. So this is called a bimeron, maybe nowadays. Has been observed, in fact, I believe, in magnets. And this is a topological skyrmion, but not as simple as the previous one. So this is there. And now we have still another skyrmionic texture. Here, this thing here, if you look over here, looks like a skyrmion. In the center, it points towards the screen. Outside, it points towards us. In between, there is this structure. So this looks like a skyrmion, except on this small region here, blown up here, it looks like an anti-skyrmion. So this is a skyrmion-antiskyrmion. It's probably a skyrmion-antiskyrmion pair, or maybe you can call it a chiral droplet. And because the topological density is drawn here, so red is positive topological density, and this little blue here is negative, but this negative thing is very negative. It goes to this is a high peak here, and this is a shallow topological density values. So if you integrate over all the space, this gives you 0. The blue plus the red gives you 0. And this is now has topological number 0, and this is a topological trivial configuration. So we have more skyrmionic textures in this system. This is quite impressive because usually in various systems, they tend to find just one soliton solution, just one soliton thing. Here we have various of them, and some of them are topologically trivial, and some of them are topological. And you can ask, well, okay, now earlier we had general results about the dynamics of topological or not topological trivial skyrmions. Do they apply here? So you can, so we saw earlier that the skyrmion is deflected perpendicular to, oh yeah, excuse me. Maybe here I want to say, right, yeah. Excuse me, so I have to repeat. So you can ask now whether the same dynamical rules apply to all these topological textures. In this case, so we can, I would say they do apply, right? But how can I kind of persuade you on that? I'm resorting now to a technique that is quite typically used in experiments. So what they do, they have a current flow, the usual electrical flow in the magnetic material, and this has an effect on the magnetization. This is called a spin torque effect, and it has the effect to excite dynamics of the magnetization. So it's a typical technique nowadays for many years in experiments, and also very nice theoretically. And if you have a skyrmion and you have a flow of current in your magnetic material, then you will see that the skyrmion does not flow exactly with the current flow, but it is deflected with respect to the current flow. Maybe I could show this to you. Why not? Can I'll switch screen. It is. I believe you can see that. And now I have a simulation of a skyrmion where you apply a current flow in the horizontal direction. And you see it does, it is dragged by the flow, but it is also deflected perpendicular to it. Perpendicular to it. Now, if you switch off the current flow, this stops. If you do the same thing with a skyrmionium, and you apply exactly the same current flow, you see that the skyrmionium is moving. Actually, it is accelerated. It is not easy to see the acceleration in this simulation, but if you follow carefully the position of the skyrmionium, you see that it is accelerated in the direction of the flow. So now this is a second dynamical experiment similar to the previous one that I showed with a field gradient, but now it is with a current flow. So it is a different phenomenon, again, a dynamical phenomenon, but similar things applied as the general dynamical laws that I discussed earlier. And now I think I have to go back. Let me. This one. I think we are back to the presentation here. Reorganize my here the windows that I have here. Anyway. So now you can ask whether also the droplet, which is a topological, trivial topological texture, skyrmionic textures, is actually following the same rules. Well, here is a droplet. We apply a current in this direction, horizontal direction. We wait and see. The droplet changes a bit due to the dynamics, but it is actually propagating in the direction of the flow. And it is accelerated. You see, if you see this interval here is a bit, this is bigger interval than larger than the previous one, etc. It is accelerated. Now, if you stop the force, this is keeps on moving. We have some damping here, so it stops after a while, but it keeps on moving after you stop the force. So the droplet follows Newtonian dynamics exactly like the skyrmionium. So this works also for any skyrmionic textures. You know, it doesn't have to be specific ones, the skyrmion or any other one. So the rule applies. Now, probably almost out of time. So I have a two more pages here to discuss more precisely what is the precise description of this propagating skyrmionium. Because you can go in a very precise description, because I said that this is a Newtonian particle, so you really have to explain, you know, it is a Newtonian particle. Okay, what is it, how exactly does it move, how it accelerates, what is its linear momentum, all that. but I think I will not say this here. I would skip it, except if there are some questions in this direction, we can discuss it. And let me go to my last page, which is a kind of, it is a remark, it will be a remark towards what seems to be a new direction. So I'd just like to discuss it briefly with you, and probably some people might be interested or might have ideas. So in the last few years, maybe in the last many years, 20 probably, people have been discussing something which they call fractons, but in the last very few years, people start to realize what these fractons are. Now, they have observed what they call fractons as particles, observed as, say, disclinations in some spin models, but also in some very different models in high energy physics, where they say that, how do they describe them? They say that these unusual particles are immobile when they are in isolation, and they can often move when they form bound states or pairs. They kind of have found that they are come up as their description comes up as in higher rank gates theories. We're not getting into the details, but you see, and they have, the basic relation that they derive there is a continuity equation, which is, for example, given in this paper, and it has this form. So you have a density, a mass, a density, so time derivative of density minus the space derivative of some flux. But here you have space derivative of something. That's the special thing about these fractals. That's what you see in the papers. So actually, what I said in this talk earlier is that the topological textures, skyrmions, for example, in magnetic materials, a similar law, if not identical law, has been derived quite a few years ago, much earlier. But here it contains the topological density of the skyrmion. Again, I don't have to tell you that this is exactly the same as that if you change the symbols. So it is gradually, as far as to my understanding at least, it is gradually understood in the community that actually the skyrmions or vortices are realizations of what now they call fractals. And that's probably an opportunity to open the field broader. Okay, so I think I'm out of time, and I hope not beyond my time. And thank you so much for your for being here, for your attention.